Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll talk about probability calibration, and these are the topics we'll go over. I will talk about briefly why it's the probability calibration is important, what it is, and then we'll look at two examples before we jump into Jupyter Notebook to perform the actual coding. So what is probability calibration? So far, we have trained several classifiers in using the supervised learning approach. And in many of these classifiers, if you look at the attributes, we can get the probability values for the classifications. So if we classify a particular sample or particular record as class belongs to class 1 or class 0, then we can also get associated probability values for being in class 1 or being in class 0. And these probability values that we get from the classifiers may not always be reliable. And so uh, that's where the probability calibration comes in. So with using probability calibration, uh, what the algorithm does is it gives us the probability values that are calibrated, and these are done through several cross-validation loops and binning, and we'll look at examples of that in a little bit. So why is it needed? Why is probability calibration needed? So it's not needed, first of all, if you do not care about the probabilities of the classified samples, or if you are interested only in ranking the samples, then the probability values are not important. But if you are interested in the actual percentage values, then the calibration would be important. For example, if you're trying to predict uh, if you're trying to predict a type of disease, and uh, if you classify it as a yes or no, that's not enough. So you need to have certain confidence in the classification. So it's the results need to be supported with probability, and there a probability of 0.4 or 0.1 makes a huge difference. And that is to say that the chances that the person does not have a disease could be 0.1 or 0.4, and that can have varying consequences. So in those cases, it is required that we have calibrated probability values. And so here is an example. First, I'm going to show just 10 data points, and here this is the plot. We have these 10 data points, and there are two classes. Class 1 is the orange dots, and class 2 is, class 0 is are the blue dots, and we just have two features as shown here. Now when we fit a classifier on this and get the probability values, the predicted probability values, this is the type of histogram we get. And because we have very few data points, the histogram is not continuous, so it's broken in here, but that's okay. We'll look at another example in few coming up slides. So here the way this calibration is done is we take the probability values that are predicted by the classifier, then bin them into maybe 10 bins. So from 0 to 0.1, 0.1 to 0.3, and so on. And then in each of those bins, we find the how many of the uh, total true classes were true. So for example, in this case, we have class 0 and 1. So within each of the bins, we calculate how many of the classes are 1 and what are the associated probabilities with those. And then from that, we can calculate the bin averages for probabilities that were predicted by the previous class, as well as the true probabilities that were that are based on the classified values. So let's say in bin 1 we have uh, values such as 1 1 0. So in this case we have 2 ones out of 3 total, so we're looking at the true probability value of 2 by 3. And in that bin we'll also have the predicted probability values from the classifier, so we can get the sum total of those probability values and then divide each of the probability values by the sum total to get the mean predicted probability values. Those would be on the x-axis when we plot the calibration curve, so which is here. So these are the mean predicted values and these are the fraction positive values, that is number of positives divided by total number of records in that bin. Now the dotted line shows perfectly calibrated case where the probabilities that were predicted by the classifier match exactly with the probabilities that are true probabilities for that particular data set. And the blue line shows the case where we have the predicted probabilities from a classifier which have variation as it goes up and down around this particular dotted line, and that is expected. So the idea is then to calibrate the probability values such that they come closer to this dotted line, and we'll see how that is done in a bit. So this is another example with 100 data points. We have more data points here. Again, class 0 and class 1 is the same. Now in this case, we have the histograms that are better than previous one, but so here we can see that there are peaks at 0 and a peak at 1, and this is like a U-shaped thing going on with the histogram. And the reason why the probabilities are pushed towards 0 and towards 1, that's because this was trained on Gaussian naive Bayes classifier, which has the assumption of conditional independence between the features, and so that's why we see this particular peaks at 0 and 1. If we use a different classifier such as SVC, then we would get a different type of histogram here. Now if we look at the calibration plot, this is also called as a reliability plot, a reliability diagram. Here we can see that this blue line again is moving along this particular dotted line as we saw in the previous example. So this is also called a reliability diagram. Now moving on, here again is an example of histogram of predicted probabilities before and after calibration. So the blue data points are before calibrations and the orange data points are after the calibration. And here the process of calibration. So how does the process work when we use the implementation in Scikit-learn? So there are two ways. One is using prefit and other is without using prefit. Here is example which shows if we are using a prefit. What I mean by that is we have the data X and Y, we split it into train and calibration set, and then or we could further split this X train into train and test set. And then what we are doing is training the classifier on the train set, and then we have a model. So we have a fitted model that can give us the uncalibrated probabilities. So we pass those probabilities on to this calibrated classifier CV class, and then to that we also so we use those there, and then we use the X-calib and Y-calib for fitting uh, this particular model, and that gives us the calibrated probabilities for this data set. Now if we have a test set, then we can use this calibrated model to fit on the test set to get the calibrated probability values for the unseen test data set. This is a code snippet where we have this new library used here, which is Scikit-learn.calibration, and from that we are importing calibrated classifier CV. And here we have again XY as the data set. I've split it into train and calibration this time. And then we initialize a base classifier, Gaussian NB, naive base, and then we fit it on the train set and use this fitted model within the calibrated classifier CV as a base estimator. And if we are using a pre-fitted model, then we need to specify that CV is equal to prefit in quotes. That gives us a calibrated model, which we can then use to predict probabilities on a new unseen data set, such as shown here by 0.75 and 0.25. Now let's get into Jupyter Notebook and see how we can implement probability calibration, and also look at how we can uh, uh, plot calibration diagram or reliability diagram. So here in Jupyter Notebook, I've imported these libraries. Uh, we may not use all of them, but I've imported them anyways. This is the one we'll be using, which is for this topic, which is calibration. And in addition to that, these are the versions that I'm using. Now for data, we have this data set created, which has two features and 1800 rows of data points. So if you look at the x.shape, we have around 1800 rows and 2 columns. And if you look at y.shape, we just have 1800 there. And we can go look at the plot, how it looks. So sns.scatterplot, and here we can specify the input for the column, the first column in x and the second column in x, and with that we can also specify the hue. I'm using SNS instead of PLT because here we can very easily specify the colors for different classes. I'm also going to set up the shape or size of each of the dots, and then also specify the value for alpha, which is 0.5 in this case. And so these are the two classes that we are going to be working with. The very first way we'll try to perform the calibration is using a prior fit. So what I mean by that is with a prior fit, and what I mean by that is we will create first a classifier, fit it to the train set, and then use the probabilities from that to perform the calibration. So we will first start with splitting the data. So we have x train, x test, so here we'll set aside data for calibration. So y train and then y calibration is equal to model underscore selection dot train underscore test underscore split, and here we specify x and y. Random underscore state is equal to 0. Now what I'm going to do next is split the train data that we have again into two sets, train and test. So I know this is a roundabout way of getting the validation or the calibration set out of it, out of this data, but this works just fine. So we have these, and in addition to this we can finally get the size of each of these. So x train dot shape, x test dot shape, and x calib dot shape. Now we have around 1000 rows for training, 300 rows for 338 for test, and then 450 for calibration. Now the first task is to fit a base classifier. So fit base classifier, and we'll initialize the variable CLF is equal to naive underscore base dot Gaussian naive base, and here we can now fit this. So base underscore CLF dot fit, this would be on the x train, y underscore train, and now we can perform the prediction. So base predict, this would be y underscore pred underscore base is equal to base underscore CLF dot predict x underscore test, then y underscore pred underscore, we can get the base probabilities here, base underscore CLF dot predict underscore proba x underscore test, and this gives us array of two columns for class. The first column is for class 0, the second column is for class 1. So we just need the second column, and then we can run this through the calibration curve to get the base probabilities and the predict probabilities for plotting. Base probability for true class, for true, and then base underscore probability spread is equal to calibration dot calibration underscore curve, and then this would be y underscore test, y underscore pred underscore base underscore probability n underscore bins is equal to 10. And so that's the first part. Now we can fit the classifier. So fit calibrated classifier, and for this now we are going to use calibrated CLF is equal to calibration dot calibrated classifier CV, and here we can specify the method is equal to sigmoid. We can use sigmoid or we can use the isotonic. So here we are going to continue with sigmoid. Base underscore estimator is equal to what we have used above, which is the base CLF, and then CV is equal to prefit within quotes, and that's because we have already done the fit on the train set using the Gaussian naive base. So with this, now we can fit this to the calibration set. So calibrated underscore CLF dot fit x underscore calib y underscore calib, and then we have the prediction. So predict using calibrated fit y underscore pred is equal to calibrated underscore CLF dot predict x underscore test, and then we have probability values y pred underscore probability is equal to calibrated underscore CLF dot predict underscore probability x underscore test, and then with this x underscore test we again need just the second column. So I'm going to get all the rows and just the second column at index 1. Then once we have this, we can now get the calibrated probabilities. So calibrated probabilities, and for this prob is true is prob true, and probability of predicted is equal to, we can get that for the calibration curve, calibration dot calibration underscore curve y underscore test probability. So it takes value of y test and then the probability values. N underscore bins is equal to 10, and we can check that. So calibration dot calibration underscore curve and RVE, and if we look at the help menu, here we can see that it takes the actual values of the class target and then the probability values. So two targets and the probabilities of the positive class only. So if we have class 1 and class 0, then this is just the probabilities for class 1 that we are getting here by putting 1. Now after this we can once we have this, we are ready now to create the plot. So plot plt dot plot, this would be prob underscore pred and then prob underscore true, marker marker is equal to, I'm going to give it a plus sign and then label this. So this would be Gaussian naive Bayes. Because we are using these probability values which are calibrated, this would be Gaussian naive Bayes, but we are using uh, sigmoid method for calibration. So sigmoid calibrated, and then the second overlay plot we'll do on this is for the perfectly calibrated. That's just going to be a diagonal line. So we can simply put 0 1 0 1 to create the diagonal line, and here line style we can specify a dotted line, so we know that that's the line representing perfectly calibrated curve. And here I'm going to label this as perfectly calibrated. Now after this, looks like I'm missing something here, label is equal to, and we still need a code there. Okay, so after that, then we have the next one is plt.plot, and this is the base values. So these are the values before calibration. Prob underscore true, base underscore prob underscore pred, marker is equal to O, and then we have a label is equal to not calibrated, and we have plt.le legend, and then we have plt.x label, and this is mean predicted probability, and then we have plt.y label, and this is fraction of positives, and finally we have plt.show. So with all this, we are in a position to plot the values and look at how the probability curves looks like. So expected CV has, so let's look at the error. Calibrated CLF of X calib, Y calib, and got prefits. All right. So here we have already done the fit on the uh, calibration. So this should be without a S. There's another error, and let's look at what this is. Has no predict prob. That's true. It has to be A after that. And again, there's a error. Classify while test prob is not defined. So let's look at this y test, which is okay. So that's not y test. I should have seen that y pred prob, and finally has no attribute PLT. I thought we have the PLT there, and now when we run this, this is line, this one. Oh, again my fault. Okay, so finally we have the plot which is also the reliability diagram or uh, calibration curve, probability calibration plot. And here we can see that the blue line is showing us the calibrated plot and the green line is showing us the not calibrated curve, and then the dotted line is perfectly calibrated. And we can see there's not much difference. There's wiggle in both cases. In fact, the not calibrated one in this case seems to have data points a little closer than the calibrated one. Maybe it's just the data points that we have chosen. Next, with this, we can also calculate a score that can be used to see how well the calibration is. That is called the Brier score. So base underscore CLF underscore score is equal to matrix dot Brier underscore score underscore loss and y underscore test y underscore, I think we gave this name, y underscore pred underscore base. Okay, y underscore pred underscore base underscore prob, then pause position label is equal to y dot max, and then we can print. So this would be for the base, and then we can get the values for Brier. This is base underscore CLF dot CLF underscore score. That's what we calculated up above, rounded to 4 decimal places. The next one we can also get the precision, and this would be matrix dot precision underscore score y underscore test y underscore pred underscore base dot round, again 4 decimal places, and then we have print. After precision we can get recall as well. Recall matrix dot recall underscore score, and this again is y underscore test y underscore pred underscore base, and this would then be rounded to 4 decimal places. And after this we can also get the f1 score f1, and this is matrix dot f1 underscore score, and this is y underscore test y underscore pred underscore base, and this again we can round this to 4 decimal places and print a dotted line, just so we can separate the next output and print a new line there. So this was for the base. We need to get the same scores for the after calibration. So after calibration, and we can specify that here as well. After calibration, and let's put that capital B colon. Okay, so here the difference is going to be what we input to this particular metric. So for this we need y underscore pred, and then this would be y underscore pred underscore pred, and instead of base CLF, this is now going to be uh, so we have up above. Okay, So this is, we can relabel this as test, and so this would be test. And here this should be the probability. So if we scroll back up, we have the y pred probability that's there, and that's what we want to use here. So y pred probability, and when we run this, we get the prior score along with all other metrics for both types of classification outputs. So we have a lower prior score is considered better, but that's not always the case. So here for the very first one, the uncalibrated, somehow it is lower than what we have after calibration, and this was after cross validation, so maybe that's why. And the precision recall and F1 again seem to be higher. Also recall and recall and F1 is higher for the after calibration, whereas precision is slightly higher for before calibration. Now let's look at the second method, which is without using prefitting a model to a base classifier. So this is without prefitting. And we'll copy the entire code from up above because that's what we'll be using. So copying all of that, paste it here, copying all of this, and then paste it down below this, and finally copying. We won't need the base, we just need the last part, and paste that here. Now within this, we do not need the calibration, so I'm going to change this to replace it by test instead of calib, and we do not need this part. And for a base classifier, we are not going to fit it, it's just going to get initialized, and we delete all of that. And with this is our classifier which takes in base classifier, and CV we do not need the prefit there, but we can specify how many cross validation folds. And then again we do not need this for calibration, this would be then on the train set directly, and then the prediction would be on test as seen here, and then we have this prediction on test, and we would not need this line which is based on the base probabilities. And finally we have the score right there. So when we run this is the, we can see the Brier score is much lower, it's 0.0996, and here we have this which is using the sigmoid method for calibration. We can see the calibration curve which is much closer to the actual, the perfect value which could have been the dotted orange line. Now if we scroll back up, those numbers are different than what we had earlier. So 0.13 and this is 0.99, so this is about 0.10, so a slight difference there. So that was it for this video. I hope in this video you got an intuition about what is probability calibration, why it is needed, and how to perform probability calibration in using scikit-learn methods in Python. If you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next final video on supervised learning in scikit-learn. That would be on the neural networks. Until then, please like, share, and subscribe. Thank you.